Howdy folks, welcome back to another episode of CS128-Honors. I'm your host, William Eustis, and today we'll be discussing parallelism and concurrency. Over the past couple weeks and in past couple lessons, I've been alluding to the fact that we'll eventually cover this topic, and so I'm super excited to finally get to it, and you'll see soon that just how kind of important I think that this discussion and this content is for any computer science, computer engineering, whatever your major is. I mean, this is a really important topic. Additionally, just because I'm so excited, I've made a seat for Andy the Android, so he'll be joining us in today's lecture. So without further ado, we'll go ahead and get started. Scoot that over there. Okay, so once again, today's goal is parallelism and concurrency. Nothing too crazy there. So I want to start off today's lecture by a quote by one of the professors here who teaches the parallel programming course. And that quote is, "Scalable algorithms and libraries can be the best legacy that we're going to leave behind from this era." And in fact, one of the big questions we need to ask ourselves is what is scalable algorithms and libraries? Or what is different about algorithms that are scalable versus not scalable? And the big difference is are these algorithms that we're going to be writing going to be applicable to future hardware and future code and the needs of future people as well? Are they going to be able to run 100%, 200% faster on machines that might allow them to do that? And to answer that question and to answer kind of what that might look like, I want to consult this graph here. And this is the last 42 years of microprocessor trend data. So generally, CPUs, each of these data points might be a single CPU. And let's look at some of the trends. So we'll start with transistors. Generally speaking, transistors are going up. Again, keep in mind this is a log plot, so they're going up by a factor of 10 every maybe 10 years or so, or 5 years or so. Nothing's really changing there. When we look at the performance of a single thread, it's still increasing, but it's starting to maybe slowly dwindle. And then there's kind of two key things that I want you all to pay attention to. And that is first, the frequency, how fast CPUs are running. Of course, a CPU can execute an instruction in one clock cycle or sometimes multiple clock cycles. But if you have more clock cycles in less time, that's going to mean that you're going to be executing more code in less time. So, increasing the frequency is one way to almost always speed up a CPU. But what we've seen is in the past maybe 15 years or so, it's become infeasible to increase the frequency any longer. Modern CPUs are somewhere in the range of, we'll say maybe 2.5 to something like 4.5 gigahertz. And what we find is it's actually quite difficult to break this. There's many reasons why. There's lots of kind of physical reasons why of dielectric breakdown of transistors. There's lots of more practical reasons why of actually having to pull the heat away from the CPU, and heat is squared proportional to the frequency. But instead of having to increase the frequency, around maybe 2005 or so, we started to focus more on increasing the number of cores. And the big idea here is rather than making a single CPU core run, 2 times, 10 times as fast and having to worry about, pulling all of that heat away and the almost impossible physics that are coming along with it, we can have more cores working on different tasks at the same time. And so because modern operating systems have, many different processes that are running, if we can parallelize the processing of these processes, we can make sure that each process is getting kind of its due attention and is operating as quickly as possible. And so that's why, modern CPUs, I think some of the higher end ones are having something like, 64 cores, 128 cores, and honestly, they're kind of growing very quickly. Before you know it, maybe a year or two from now, we'll start to see some consumer CPUs in the 200 range. And so when it comes to scalable hardware, it doesn't necessarily mean that our code needs to be shorter or fewer instruction cycles. Very often it can mean maybe it's leveraging more cores at once, or maybe we're making sure it can be run on a single core quickly as fast as possible. Those are kind of two different things, but what we see, single cores, they're starting to speed up less and less. While, we're still going to be able to have more and more cores on a CPU, at least for the near future. Some say that, and it is probably true, there's probably some limit for this around this range, but we'll see. And there'll be other ways to make things more efficient after that. Okay, and of course this ties in very closely with our discussion of parallelism and concurrency, because if we want our code to be scalable, we need it to be concurrent, and we need it to maybe be parallel. So let's define these two terms explicitly. First, of course, is concurrency. Concurrency is the idea that different parts of your program are executing independently, while parallelism is the idea that different parts of the program are executing at the same time. Maybe here's a quick graphic, if that could help. Concurrency meaning you work on some process for some time, and then you switch, and you work on another process, you switch, you work on another process, you switch, and you switch. While parallelism says all of these things can be worked on at the same time. Now, there are many reasons why concurrency is also faster. You might say, hey, isn't it expensive to switch? The answer is yes. And, at the end of the day, you're still kind of doing the same amount of work. Why not just do this, and then this, and then this? And the answer for that is there's many operations that are required that are slow. So if you need to read from a hard drive, for example, right here, this could take the equivalent of hundreds of thousands, millions of clock cycles even, before your program can actually continue, just to read, maybe a relatively small amount of data. Hard drives are slow to read in the CPU scale of things. And so while we're waiting for that data, we can go work on some other task. And then eventually when that data is ready, we'll request to begin work once again. And so what this does is it minimizes the downtime of the CPU, right? So concurrency allows us to make the most out of downtime. Parallelism, on the other hand, is a little bit more straightforward to understand where the acceleration comes from. We can accomplish multiple tasks at once. Okay, concurrency isn't easy, and I might even go as far to say as concurrency is hard. And let's just give a quick example. So let's say we have some global data here that has some 0 in it, and we have some process that wants to read it and increment it by 1. Okay, so first we perform this read, and then we perform the write. Nothing too crazy there. However, let's look at another example with some concurrent code. So maybe this process, or maybe another way to say this could also be a thread. I think either of those could be applicable in this case. Reads this value, but then before it can perform the write, an interrupt occurs. And this could be saying, some other process saying, hey, give me attention. I'd like to do my operations now. My data has loaded. The user has clicked somewhere. The user's typing. The user has, done something, right? I mean, there's a million different things that can be interrupts. And now some other process starts. And just by chance, this process also interacts with this global data. And so this process is now going to write some value to this global data. And then once it's done that, we'll return back to our continuing process. But the issue occurs that we've already read x. X is on the stack, and the value of x is 2. Or rather, x is probably in a register. And the value of x is 2. And so we're about to write, the value of x is 1. And so we're about to write 2 into global data, but global data is currently 10. And so should it be 10? Should it be 11? Should it be 2? Who knows? There's no correct answer. And there's a couple ways to solve this. One way that is kind of common is to define this as a critical section in languages that are not Rust. And so then if an interrupt occurs, you block the interrupt. Of course, this isn't perfect. If you're doing if your entire program is a critical section, which could prevent this, then that also means if you, for example, try to click, your computer might not respond for a while if you had maybe only a single thread or only a single execution there, because your program is so focused on executing this and it's blocking all of the interrupts that it can't take a moment to process whatever your click should do. So obviously that might not be the best thing. But the big idea here is once this critical section ends, we can then relinquish control into some other process. And let's look at just a couple of these issues because I think they're very important and they're more common than you would think. The first one that we've already seen is what we call a race condition. which is we have two threads or two processes who are trying to access the same resource, but are doing so in a different way. So thread A and thread B both access resource 1, say some piece of data, some file, something like that. Thread A edits it in one way, thread B edits it in another way, and then let's just say they both try to increment. So they're both trying to perform a write. Of course, thread A is going to try to write it to be 3. Thread B is going to try to write it to be 4. So who's correct? And the answer is basically whoever gets there first, which, is impossible to determine. It's how your operating system decides to schedule these threads, which is not necessarily something that you always know. And so there really is no correct answer, and you have undefined behavior, which of course is bad. There's also deadlocks. We'll say thread A, of course we mentioned, you can kind of lock down, or one way to approach this is you can deny other threads access to certain resources while you're accessing them. So instead of doing maybe a critical section, we can just have, another piece of data saying, hey, this is in use right now, or hey, this is not in use right now. But of course, this comes with its own issues. Deadlocks is a common issue with this. So thread A takes control of 1 and 2, thread B 3 and 4. And then maybe thread A needs resource number 3, and so it requests it from B. B denies because it's still using that, but B needs access to number 1, resource 1, and so it requests it from A, but A is still using it. And so basically they'll just keep going back and forth, requesting and denying another until you decide to close the program. So yeah, just one example, kind of poor memory safety and poor concurrency can lead to programs never doing anything. There's also live locks. You might say, haha, oh, Eustis, I'm so smart. Why don't we just say, if something requests access, we'll just give it to them. I don't care if I need it. We'll go back and we'll get it ourselves later. We'll give it to them. Then we can run into a similar issue called live lock, which is, anytime there's a request, we'll let you have it. But then, of course, we're going to need it right afterwards, and so we'll request it as well. And then thread A will request it. And you might say, okay, what if we have some like hierarchy of, thread A is more important than thread B, or maybe thread B can't request it after a certain amount of time. And those are solutions. You would be correct. Of course, nothing is perfect. Eventually you're still, if you say thread A is more important than thread B, then thread B is what we call in a state of starvation that we'll see in one moment. But if you say, instead that thread B just has to wait a while, then, that works, but thread B isn't doing anything during that time. So maybe it's less efficient. And then finally, starvation, which is, thread A accesses 1, 2, 3, and 4. Thread B says, here you go. And then thread B keeps trying to access again and again and again, but it never gets it because thread A is using these forever, or at least maybe for a long time. And so all of this time is sort of wasted on thread B, which could be running on a separate core or a separate thread. Okay, so concurrency is hard. There's many issues that we can kind of run into, and ownership will help us with a lot of these. And we'll explore more about specific cases of how in a bit, but for now I actually want to start to discuss how we implement threading in Rust. But this short discussion on concurrency and parallelism is something kind of very important. And specifically, it's these 4 cases that you might need to either pay attention to or just keep in mind because they're important. You'll use them in all sorts of classes in the future. 231, I believe, 241, or sorry, 233, 241. I'm not sure what other classes, 433 for sure. I use it in 391 a ton. Now I use it some in 411. Okay, so ownership helps with a lot. And so let's discuss some quick terminology before we move on to the more kind of content heavy part, or code heavy part, maybe I should say. And we're good on time, so that's nice. Okay, so an operating system manages processes. Nothing too crazy there. A process is maybe what we call a program that's being executed, right? A program, of course, is something on your hard drive. It's not necessarily doing anything, but when you execute that program, it's going to create a process. Sometimes multiple processes. A process can have many threads. There's probably a limit. It depends on your operating system and many other things, but processes can have threads. Each of those threads can do something different. Each thread has its own registers, has its own stack, but might execute similar code, different code, but they all live under the same process, which has specific data and specific files that are going to dictate what code they're actually executing. And then threads, at the end of the day, are execution of code. So a thread is some stream of code that is being executed by your CPU. It is the registers in the stack that make up the current state of the program. It is all of these things. Wonderful. Okay. Okay, I just noticed that I moved it over so that my camera wouldn't block it, but then I put it on a different slide. So here you go. Okay, so let's talk about threads in Rust. This is going to be a quick example. And we'll be discussing this for, many lectures now, so don't worry too much, but do try to pay attention. So step one is the imports. Of course, threads are built into Rust, and so we import standard thread. We'll also import standard time duration. You don't actually need standard time duration to use threads, but we're going to use it here in this thread.sleep, or thread sleep function, just because we like to. Okay, wonderful. So let's break down what this code is doing. We have a main function. We call this thread.spawn function. And then what the heck is this? Eustis, I've never seen this before. And you'd be right. And so I'm going to have a quick aside here where we talk about closures. And in the last, I believe, 2 weeks of the course, we'll actually talk about closures a lot. Closures are a concept from functional programming. Basically, it is a function that you allow to be a variable. And so just 2 quick examples. Y'all don't need to know this in depth, but it'll be helpful just to reference it. At the end of the day, once again, I'll remind you a closure is a function. Okay, so for this specific example, we create some closure and we call num, or we pass the closure to the num value, and the closure is going to return an int32. This is the code for the function, or for the closure. It will print calculating slowly, it will wait 2 seconds, and then it will return num plus 1. So when we call println closure 3, 3 will get passed into num, it will wait 2 seconds, and then it will return 4, ideally. And in fact, this is what we see. So just one more quick example. Here's kind of a gradient, I'll say, from a function format where we have, what are your inputs, what are their types, what is the return value, and then you have your semicolons for the scope. And then we slowly turn it more and more into a closure. And I believe all of these are valid too. So, we can replace these equals parentheses, or we can replace the parentheses with equal sign in the bars, keeping everything else the same. Of course, we'll also need a semicolon now because it's no longer kind of in the global level. We don't actually need to specifically type the return value in the input value. These are actually typed at runtime. So if you call add1v3, for example, with u32, then add1v3 from that point on will be u32, and the program will figure that out whenever you call it. Also, it will return, whatever the return value is. Of course, if you then try to call it with something that is not this, it'll error out because it says, hey, you already made it so that I'm u32. I can't be something else. And then finally, if it's a one-liner, you don't actually even need these semicolons. Of course, you'll need it for multiple lines, but if it's not multiple lines, you can just put, x plus 1. Okay, so that's how closures work. Big idea is it's a function. Okay, so what are we passing into this function? Nothing. We're not passing anything into this function. Of course, I will mention Rust is smart enough where if you use some variable in here, so if I have like right here, for example, let x equal, 5, and then you use x within the thread, Rust is smart enough to actually infer that you might want to pass x into this thread, and it'll try to figure that out for you. But we'll actually look at an example where that can cause some problems at the very end of this lecture, and we'll explore this way more on Monday. Okay, so what's happening here? We spawn some thread, and that thread is going to execute this code. And what this code says is for i is 1 to 10, print the number from the spawned thread, and then wait 1 millisecond. And so we'll print 1, 2, 3, ... 8, 9. Of course, non-inclusive. We don't include the 10. And then after that, or at least in the code after that, we'll also do no spoilers. I clicked twice by accident. We'll also do a for loop from 1 to 5. And we'll say hi number blank from the main thread. And then we'll wait for 1 millisecond. Okay, so take a moment and really ask yourself, what do you think this is going to do? It's not live, but I like to do pauses anyway. So, there's different ways of thinking about this. You can say, okay, well, clearly Eustis, this is some sort of trick question. The thread, we just talked about how these kind of work concurrently. And so what we'll get is like the thread is going to type 1, and then this is going to do 1, and this will do 2, and this will do 2, and this will do 3, and 3, 4, 4, 5, 5, nothing, 6, 7, 8, 9. And you'd be very close. And actually, maybe some of you think, okay, well, that's true, but this is first at the end of the day. And, we have this handle thing, and I'm not really sure what that means, but at the end of the day, we have this code. It's first. We're going to print 1 through 9, and then 1 through 5, or 1 through 4, I should say. And so let's see what we actually get. Okay, so we get 1, 1, 2, 2, 3, 3, 4, 4. Main spawned, main spawned, main spawned, main spawned. So pretty nice behavior. Some questions to ask. Why don't we get to 5? In fact, where's 5 through 9 from the spawned thread? And the answer is this handle is what actually sort of controlling the spawned thread. It's what's keeping it alive in a way. And when we get, after we finish 4 and we get to here, our main thread has died. It's done. It has no more things to do. This handle goes out of scope. It is closed. And so this thread along with it is killed. And so after the number 4 is printed in the main thread, there's nothing left to do, and it ends. But if you run the program again, sometimes you'll get this, and sometimes you'll get something else. There's actually no guarantee from what you'll get. In fact, sometimes I'll just run it one time after another just to see what'll happen. And in this specific case, we got 1 from the main thread, 1, 2, 3, 4, 5 from the spawn thread, so maybe the main thread went on to do something else. And then 2, 6, 3, 7, 4, 8, so close to getting the 9, but we don't get the 9, and then the main thread dies. And in fact, there's kind of any number of things that could happen. The output of this is undefined, right? One way that we can kind of think about this is the console is some shared resource, and we have 2 threads that are writing to that shared resource. And of course, we have no way of saying, okay, this is a critical section, don't do anything while this is doing something, because we want to print all of these first. It doesn't really make any sense to say only one person can print to the console at a time. But, maybe just to tie that back to these sort of race conditions, I mean, this is, at the end of the day, what we're seeing. Okay, but, of course, you might say, or I might remind you that not all hope is lost. And, if you need to be able to execute one code before some other code, you can always do that. And we'll do this with this thing called handle.join, and then we'll unwrap as well. I'll ask all of you curious folks why we do the unwrap here in a bit, but the big part is this handle, once again, is what's kind of holding on to this thread. And when we call .join, what we're going to say is, hey, when you get to this line, which, remember, is in the main thread, when you get to this line, wait for the other threads to end. Okay? They're still maybe doing work. We need to make sure that they're done before you can continue. Maybe they're working on processing some other data that you're going to use in a bit. Maybe, we just want to make sure that they finish their task, and maybe it's not even necessary for the main thread later. Okay, and then why do you call the unwrap? For the curious of you, this is because if the thread errors out, we need to be able to actually propagate that error outwards through the main thread. So, fun little tidbit there. Okay, so what happens when we call this? Generally speaking, it seems like I didn't actually put the print, but it'll be something along the lines of, 1 from spawn thread, 1 from main thread, ... 4 from spawn thread, 4 from main thread, and then 5, 6, 7, 8, and 9 from the spawn thread. Basically saying the main thread gets to its 4, they're trading off pretty equally, and then eventually the main thread has nothing else to do except for wait. And so that's what it does. Okay, so another quick question to those curious. What will happen if we put the handle.join.unwrap here instead? And I'll give you a moment. Okay, so hopefully this one isn't too complex. If you say, hey, the spawn thread is going to print 1, 2, ... 9, you'd be pretty close. except you actually missed the fact that I changed the 10 to a 9. And so, it'd actually be an 8. But otherwise, the idea is the same, which is it'll print 1 from the spawn thread, 2 from the spawn thread, all the way until 8 from the spawn thread. And then it'll print 1, 2, 3, 4 from the main thread. Okay, and just on time, too. This is so perfect. Okay, so quick recap. We can use thread.spawn to spawn threads. These threads can go do other work. Again, not quite at the same time. We have to remember it's concurrency, not necessarily parallelism here in this specific case. I might use the terms interchangeably, so please don't yell at me if I call one thing another thing, just for simplicity's sake. And then we can use the handle.join, or really, the .join function is the key here, in order to wait for these threads, or to synchronize these threads is another term. Okay, quick sneak peek for tomorrow's lesson, or Monday's lesson, I should say. What happens here? And I'll give you a hint. This code does not work. This code will error out, and it will yell at you, and your computer will explode and catch on fire, and then you will cry. Okay, so for those of you who are sort of extra curious in this topic, I encourage you to give this a little bit of thought before Monday. It's quite an interesting little problem. Of course, this is from the Rust docs, so you could probably find it out yourself, but no cheating until Monday. Until then, I'll see you all. If you have any questions, please let me know. And I'm excited to keep talking about parallelism and concurrency. I really love this topic. All right, bye-bye.